Now let's look at the second part of solving this optimal resource allocation problem. And let's first recall what we've done in part 1. And in part 1, we have done this, that we found V2 of A is going to be equal to 1 plus alpha squared and minus 1 plus alpha squared over A. And from the forms of V1 and V2, and we propose, we guess that Vn of A has the same pattern. That means we can have An minus Bn squared over A. Our task now is to determine if we can find these two sequences of numbers n bigger than or equal to 1. Okay, so to 1. And how do we do that? We will plug in the form of Vn minus 1. So Vn minus 1 of A minus x, because that's needed in the formula. If this were correct, then we have An minus 1 minus Bn minus 1 squared and over A minus x, right? So that's what we have. And then we want to solve the following problem. So Vn of A is equal to maximum x between 0 and A. And we still have ux, so 1 minus 1 of x, and plus beta over here. And we put Vn minus 1 over there. So we're going to have An minus 1 minus Bn minus 1 squared over A minus x. Okay. And we see we now have more parameters. In fact, in this optimization problem, you will see all these things are parameters. Capital A over here is parameter. Beta is parameter. An minus 1. All these things are parameters. And the variable we have over here is x. So we just try to remember that we are maximizing this function. F of x is equal to 1 minus 1 of x. It helps if we actually call this whole thing a new function. That way, we can use the knowledge from calculus. Okay, so this is the one. All other things are constants. So now we do the same thing. We try to take the derivative, find the critical value, f prime of x, and that's going to be the same thing, really. First one, 1 of x squared. When we take the derivative of the second one, remember beta and a n minus 1 is constant. So remember this, these things are all constants. These are constants, right? So when we take the derivative, we're going to have negative beta and Bn minus 1 squared is constant. And take the derivative of this 1 over 1 minus x. Just to be very careful, we will have a minus x squared, but it's going to be negative 1. And then multiply by another negative 1 since a minus x, remember derivative is negative 1. Okay, so now we let derivative to be 0. Okay. And then we have 1 over x squared minus beta Bn minus 1 squared over a minus x squared over here is equal to 0. Let's also do the following thing. Let beta to be alpha squared, right? That's the notation we used before. You will see the advantage of doing this. Of course, this is problem specific. It's not that we all the time want to make this kind of change. And then we have 1 of x squared is equal to alpha squared Bn minus 1 squared. And we have a minus x squared. Because everything we have over here are non-negative, so we can take the square root. Then it means 1 over x is equal to alpha bn minus 1 over a minus x. Remember, we still want to solve x, right? So we multiply 1 minus x over here, and then here we have alpha bn minus 1 x. Okay. And we isolate x out, so a is going to be equal to, add x both sides. This is what we had, in fact. And then this is going to be equal to 1 plus alpha bn minus 1x. We focus on x and solve x, so we have x is equal to a over 1 plus alpha and bn minus 1. This is very similar to what we had in part 1. So let's call this one our candidate for the maximum. And then we still look at the second order derivative test. Second order derivative test, we will have again negative 2 over x cubed. We need to look back the derivative over here. Yeah, and then take derivative one more time. We will again have negative, many negative numbers, but it's okay. Beta bn minus 1 squared, and we have negative 2, and we have a minus x cubed, and multiplied by negative 1. Okay, so we end up with this again. It's a negative second order derivative. So x star is equal to a plus alpha. Again, by the same reason, this is in the interval, 0 and a is the maximum. This is actually necessary. Maximum point, or the critical value, we have verified. So now we're going to again plug it in. So what we have over here is 1 minus 1 over x. This is the first term, and this is going to be 1 minus 1 plus alpha bn minus 1 over a. We still have the second part. Let's just try to do that part carefully. So what's going to be beta of v n minus 1? A minus x. We do the following thing. A minus x, do the computation. Okay, we plug in x star. So it's going to be a minus a over 1 plus alpha bn minus 1. Common denominator again, and then this is going to be 1 plus alpha bn minus 1. Factor a out, and common denominator, n minus 1. This is, in fact, our second time of computation now. So this is going to be a alpha bn minus 1 over 1 plus alpha bn minus 1. Okay. Just be very careful about these computations. If you just make one small error, then you're going to ruin everything. So just be extra careful. And what do we do now? So we want to find what's going to be v n minus 1 of a minus x. According to our assumption, this is going to be our a n minus 1 minus b n minus 1 over a minus x, right? That's what we have. So we plug in this formula, and this is going to be a n minus 1 and minus, take the reciprocal of this, then we have b n minus 1 squared, and this one over here we have 1 plus alpha b n minus 1, and now this a times alpha b n minus 1 is in the denominator. Simplify a little bit. This is what we have. We have a n minus 1. We see we can actually cancel one factor of bn minus 1, right? And then we have over here bn minus 1. then we will have over here 1 plus alpha Bn minus 1 and negative sign over alpha times A. So this is what we have. Now we look at what's going to be Vn. Vn of A, plug in the maximum value, then we have 1 minus 1 over x squared, this part. So let's copy it over here. So it's 1 minus 1 plus alpha Bn minus 1 over A. Okay, and we have over here plus beta, that's alpha squared. Okay, and then we have over here this Vn of Vn minus 1. So we're going to have over here An minus 1 and minus Bn minus 1, 1 plus alpha Bn minus 1. Yeah, that's okay. This is the multiplication, and divided by alpha A. And we need to simplify. So if we simplify, this is going to be 1 minus 1 plus alpha Bn minus 1 over A. And this part we have alpha squared and N minus 1. And when alpha is cancelled, so we have minus over here alpha Bn minus 1, 1 plus alpha Bn minus 1. Yeah, that's okay. And then over A when alpha is cancelled. So that's what we have. And again, like the previous step, we put them together. So we have 1 plus, collecting the terms, the like terms. So this is the one, the constant one. And then second one has A inside, so it's 1 negative. If we look at the common factor carefully, this is exactly 1 plus alpha Bn minus 1 squared over A. Okay. Now what we see is that we have the same pattern that we started with. And in fact, remember that our assumption is Vn of A is equal to An minus Bn squared of A. They look exactly the same. So what we need to do now is just say, well, these two formulas, they should match. That means An should be equal to alpha squared An minus 1 plus 1, right? And remember, A1 is equal to 1. And also Bn, we should have, it's inside, right? Bn is going to be alpha Bn and plus 1, right? And B1 is also 1 because we started to remember that V1 of A is equal to 1 over 1 minus A, right? That's what we have. Now, when you look at these two recurrence relations, we realize we have solved them before. And I'm going to skip this step because we already know in the past how to solve it. And for Bn, especially, that's going to be the easiest. Bn, this is minus 1. Okay, so Bn is going to be equal to 1 minus alpha to the n over 1 minus alpha, right? That's exactly the sum of the geometric sequence. And for An is going to be equal to, we see the common ratio is alpha squared, so it's 1 minus alpha squared to the power n and 1 minus alpha squared. So these are the ones we have. So now we are finally done. We have solved the problem that we have Vn of A, the maximum value when we have n periods and the initial total amount of resources, capital A. This is the maximum achievable utility or return, and it's going to be 1 minus alpha to the 2n over 1 minus alpha squared, and minus 1 minus alpha to the n and 1 minus alpha squared, bn squared over capital A. That's what we have. Or if you want to swap back to the square root of beta or alpha, then we have 1 minus beta to the n, 1 minus beta, and minus, when you have a compound fraction, it's probably better we actually try to bring it down. This is going to be 1 minus root beta to the n over 1 minus root beta, and the whole thing squared, okay, and multiplied by 1 over capital A. And that's the end of solving this problem of finite period with discount factor for resource allocation.